The idea of last time was this idea of looking at what's called the second partials test, which is really a classification of critical points. And so when we talk about the second partials test, talk about classification, we're really looking at saying what happens locally. So we can say, well, something is a local min, or a local max, or it's a saddle. And what we're doing is we're saying, I can use the behavior of the function nearby, dictated by what I see happening with the derivatives, to indicate what's going on. Now, as a consequence of the fact that I'm using a local approximation, that's what we're doing, is we're doing that second order Taylor polynomial. It's a local approximation. It really does say I can only say something about local behavior. So the goal today is to say, well, look, what if I don't want local max min? I want global max min, or you might say the absolute max and absolute min. How do we go and do that? All right, well, there's a small catch before we even begin our conversation, is that there might not be any global max or min. You know, we might have a function which never does have a max or min value. So we're going to go with a very complicated example to demonstrate this. Suppose our function is x plus y. All right. Well, maybe not too complicated. I think we can understand what that function is. It says I'm plugging in two values and I add the two values together. But the key here is to look at the domain. See, our domain says what? It's not just any x and y. X goes between 0 to 1 and y goes between 0 to 1, but I'm not going to include my endpoints. Or really, I should say, I'm not going to include my edges. Because if we think about this in the xy plane, what's happening is that my domain looks something along the lines of the following. It's going to be, here I have x equals 0, x equals 1, y equals 0, and y equals 1. That's the domain. This is my square. Well, that's not quite the domain. The domain is everything that's on the inside. So there's my domain. All right, so I have my domain. These are the points I'm allowed to plug into my function. Now let's think about what's the largest possible number I can get for my function x plus y on my domain. And let's think about the smallest. Maybe smallest is easier. What's the smallest possible number I can get?
0.
Can I get 0? No. See, I can't get 0 because 0 is out. It's out of my domain. This origin would be a fantastic candidate. And I can get close to 0. And so I can make x plus y small. But here's the catch. I can get closer. You see, no matter how close I get, I can move a little bit closer. That's the idea of this continuity thing, is that I can always move closer and closer and closer. And so I'm getting closer and closer to this point, this value of 0, or rather this point 0, 0, which would give an output of 0, but I can never reach it. Because if you think back to our language, that point 0, 0 is a boundary point, but it's not in our set. So that's the problem, is I can't get close, I can't reach that origin, that 0, 0. Similarly, is there a global maximum? Well, the answer is if we had a max, we'd want x and y to be large. So the max would happen in the corner over here. But the corner, that upper right corner, it's not in our set. It's outside our domain. And I can always get closer and closer and closer. So what's true is that 0 is less than x plus y is less than 2, because that's for sure. But I can get as close as I want to 0. And I can get as close as I want to 2. So I never attain a global max and a global min. So when we talk about attaining a global max and a global min, it says there's a point in my domain that I can plug in, and that's the largest I can get from any point in my domain. it doesn't mean that we're not bounded. Just because I don't have a global max or global min doesn't mean, well, I'm an unbounded function. It just means there's no point that achieves the largest value. All right. Well, that's kind of puts a damper on affairs. The good news is, maybe if we can avoid this situation, life gets better. And it does get better. All right, so what's our main problem? Well, the main problem is that we can get close to an input that we want to put in, but we can't reach it. So in terms of the language that we use, there could be two issues. One is that we might not include our boundary. So that would be if our set wasn't closed. So we don't want our set to be closed. The other problem is that we might have to keep going forever. Well, that could happen if it was not bounded. So we'd want our set to be bounded. Well, it turns out, fun fact, if we have a reasonable function, reasonable here being continuous, and our domain is closed and bounded. So closed says I can always get to my edges. I include my edges. Bounded says I can put my whole domain inside some big circle. In other words, I can't get arbitrarily far away. Then I attain a global max and I attain a global min. Now, proving this is very, very hard. This is a very non-trivial fact. And if you want to prove it, there's a wonderful sequence of courses that you can take. And by the time you finish those courses, you'll be a math major. And or you can take it on faith, whichever one you prefer. But for right now, for our class, we'll take it on faith. So that if I have a function which is continuous and I have a closed bounded domain, I know that there's a global max and a global min out there. This is very useful because it sort of gives us the whole game. Because now we know if we're in this setting, continuous function, closed bounded domain, I say I know one exists. And how do I go about finding it? Well, we're going to use what I like to think of as the Santa Claus approach. We're going to make a list, and then we're going to check that list, and then we're going to get our answer. So how do we go about it? So we know that there is a global max and global min out there for us to find. So we say, well, let's start looking for where it could be. Now, it has to happen at what we would call critical points. So we say, okay, well, let's look on the inside. So the inside of a set, the interior, that's away from the boundary. Now I say, well, if I'm a max or a min, a global max or a global min, and I'm on the inside of my function, I also have to be a local max or a local min, which means I have to be at a critical point. So we're going to find where does the gradient equal 0 or where is it undefined. So that says, let's look on the inside. Maybe the point we're looking for is there. Step 1. So we're making points. We're making our list. Step 1 and 2 is about making the list. The second step, it says, okay, you looked on the inside. You don't have to look on the outside because the outside is not in our set. We don't care about what happens outside. But we have to look on the boundary. A lot of times it will happen that the max or the min will occur on the boundary. Now, how do we work on the boundary? Well, the answer is the boundary shrinks the dimension. So what do I mean? Well, we'll do a little picture here. If I'm looking at a set, and maybe our set is a circle, and originally we say, well, look, the domain might be all the points in and on that circle. So the shaded part in the center, that's the interior. The circle on the edge, that's the boundary. Now when you look at the circle and you say, the circle itself, that boundary edge, it's a one-dimensional thing. It looks like a curve. The whole interior is a two-dimensional thing. So what happens is when we work on the boundary, we get to reduce dimension. Go down from something two-dimensional to something one-dimensional. Now, if we ever had to do a problem where we were doing optimization of a 3-variable function, which we could, we'd get to do lots of this, where we say, okay, let's first work on the bounding surfaces. Go through from a 3-dimensional input to something which is 2-dimensional. Go from 2-dimensional to something which is 1-dimensional, and so forth and so on. Okay, so we find the points in the boundary. Don't forget corners. Corners are always included as critical points. Okay, so these two steps, step 1 and 2, that's our make a list phase. Step 3, now we say our global max and our global min are on the list that we've created. I just have to figure out which one. So we're going to plug all the points that we found in, and we're going to see what the result is. All right, and the final step is we just say, okay, what was the biggest number? Whatever the biggest number is, that's the max. What's the smallest number? Well, whatever the smallest number is, that's the min. And we're done. Finished. All right. And that's our theory for today. The remaining time is practice. So any questions about the theory? And I will tell you that these problems will test your patience. And we're hopefully going to be able to get through 3 problems in the remaining time. So you probably are like, yeah, cool. All right, so away we go. All right, so we'll warm up to it. So find the global max and the global min for the following function. F of xy is x squared plus 2y squared minus xy minus x minus 3y, where the domain is all x between 0 and 5 inclusive, and for all y between 0 and 3 inclusive. Okay. Well, let's talk about our domain. So what does our domain look like? Yeah, it's a rectangle. So our domain will be a rectangle. And in this case, it's a rectangle where I go 5 units in the x direction and 3 units in the y direction. So I go from x equals 0 to x equals 5, y equals 0 to y equals 3. And then that's the edge. Of course, we also have all the points in the interior. Okay, so there's our domain. All right, so we're ready to start our process, which means we're going to make a list. So I'll have my list over here, which will continue to expand as we go through. Step 1, look in the interior. When I'm looking in the interior, what do I do? Find the critical points by doing what? Gradient. So the interior comes from the gradient. So we should find the gradient. What is the gradient of f? 2x minus y minus 1, comma, 4y minus x minus 3. Okay, good. So there's the gradient. Now we're going to set this equal to 0. So saying the gradient equal to 0 is really the same thing as saying the partial derivative is equal to 0. It's the similar process we went through last time when we were looking about, let's find the critical points. So we get really 2 equations. So the first one I can write as 2x minus y minus 1 equals 0, or 2x minus y equals 1. And the other equation I can write that as minus x plus 4y equals 3. All right. What happens next? Yeah, we solve for x and y. Now there's lots of ways you can do this. One way you can do this is you can say, I'll substitute in. Another way you can do this is you can combine things together. But this is kind of a more straightforward one because there's no squares, there's no cubes, it's linear combinations. So for instance, one thing you could do is if you took the second equation and multiplied it by 2 and you added it, what would happen would you get 2x minus 2x, which would cancel, minus y plus 8y, which is 7y, and then 1 plus 2 times 3, which is 6, which is 7. So 7y equals 7, or y equals 1. And once you know that y equals 1, what should x be? X should be 1, which says that there's a point 1, 1. Now, here's the question. Do we add 1, 1 to our list? And how do we know whether or not to do it? Check if it's in the domain. Now, not every critical point you find will always be in your domain. So you have to check. Now, it turns out that 1, 1 is in our domain. Because 1, 1 is in our domain, we add it to our list. If we had found a critical point, which, say, had been over here, what do we do with that point? Nothing. It doesn't make the list. The only thing that makes the list are points which are in my domain. Okay, so we've now checked the interior. That wasn't so bad. What's next?
Check the boundary.
You have to check the boundary. Now, when you check the boundary, don't forget your corners. So let's just throw in corners right away. Where's this bottom left corner? Yeah, that one's easy to find. 0, 0. How about this corner? Yeah, it's 5, 0, because x equals 5, y equals 0. How about this one up here, the 0, 3, yes. And the last corner, in upper right. 5, 3. X equals 5, y equals 3. Good. It's always good to remember to throw in the corners because sometimes it's easy to forget. Okay, so we've got now a longer list. Now, we're not done yet. We have to check the sides, which means we have to check every side. So how do we check the sides? Well, what we do is we're going to go through and do them one at a time. Which side would you like to start with? We can call them left, right, bottom, top. Left. Okay. So the left side. Now the left side corresponds to x equals 0. So what we can do is we can say, put in x equals 0. And what's going to happen? Well, our function no longer is a function of x and y. It's only a function of the y, because we've set x to be 0. So I can now think on the left side, I can look at it as just a function of y. So I'll call it g of y. But really it's f of 0 comma y, which would be 0 plus 2y squared minus 0 minus 0 minus 3y. So that the function on that left edge is 2y squared minus 3y. Now, what do I do? Well, that's what the function does. I want to find, is there something that's critical about this? Which means, what do I do?
First derivative that's with just a normal function.
Take the first derivative, g prime of y. All right, take the first derivative, 4y minus 3, set it equal to 0, and what do you have? Y equals 3/4. Well, we know that x equals 0, y equals 3/4. That would put it about here. Does that make the list? Yes, it does. 0, 3/4. Okay. Well, that's one of the sides. What's next? We still have the right, the top, the bottom.
Right.
Bottom? When we're on the bottom, what's true? Y equals 0. So now what I can think of is really I have a function of x, which is found by f of x comma 0. Well, okay, so that's going to be x squared plus 0 minus x minus 0. So x squared minus x. So that's the function. Take the derivative, g prime of x gets 2x minus 1, set equal to 0. Which value of x do we care about? 1/2. Well, that would be about there. Okay, so what's the critical point? 1/2, 0. And it's in the domain, so we add it to our list. Okay, what's next? Right? Well, I heard someone say right first, so we'll go with right. What's true about the right side? X equals 5. So we're going to have a function just of y. All right. So we have some function of y, which is f of 5, because x is 5. That doesn't even look like 5 anymore. Okay. F of 5 comma y, which is, okay, so here we go. Well, we're going to have 25. All right. I'll put the number down later. 2y squared. Then we have minus 5y, minus another 3y later on, becomes minus 8y. And I haven't forgotten the 25. We're also going to subtract 5, which makes it 20. Okay, take the derivative. G prime of y would be 4y minus 8. Set that equal to 0. Says y should be 2. Now, is that in our domain? Well, it would be x equals 5, y equals 2, which would be here. That is in our domain, so we add it to our list. 5, 2.
So is the negative 8 in the first line and the negative 8 in the second line, are those the same number?
Yes, because I forgot to put a y here. All right. Are we done? No! See, these problems are fun. Just when you think that you're done, there's one more side to go. Okay. Which is the last side? The top. What's true about the top? Y equals 3. So we're going to have just a function of x. We call it g of x. So g of x, which is f of x comma 3. Okay, well, let's see what we're going to have. We're going to get an x squared. All right, that's good. Then we have 2y squared, which will be a number. I'll come back to that. Minus 3x minus x. So that would be minus 4x. And then this minus 3y is the number. I said I'd come back to the numbers. Okay, so 2 times 3 squared. 2 times 3 squared would be 18. But then I'm going to subtract 9. So that leaves me with 9. All right, what is g prime of x? 2x minus 4. Set that equal to 0. Get x equals 2. Which puts us around here, which is a point in our domain. So we add it to our list. All right. Have we accounted for everything? Yes. We got the interior. We checked the gradient equals to 0. We got the corners, because we always know that corners should not be forgotten. We checked every side. We've made our list. Whew. Now, before we continue, I want to point something out about the process of making the list. When I took the gradient and I set it equal to 0, I got a critical point. Did I test that critical point? Did I use the second partials test? I did not. When I took the derivatives on the edges, the curves, did I bother to check whether these points were mins or maxes? I did not. Why did you not do that? Well, because it's useless to do that. That's extra work that you don't need to do. So when you're doing the process of finding a global max or global min, don't bother with local properties, because that's not important. All you care about is what's the largest value. We don't care whether or not it's a local min or a local max. So you want to make sure, let me do the right work and the right amount of work. All right, so steps 1 and 2 are done. We found all our points. What's our next one? We're going to plug everything in. So we're going to now plug every one of these points in to our function. Okay. Thankfully, I left myself some room. Well, 1, 1. That's not so hard. That's 1 plus 2 is 3. Minus 1, minus 1, minus 3. So that would be negative 2. 0, 0. I like that one even more. That's 0, plus 0, minus 0, minus 0, minus 0. That's 0. 5, 0 is something. Ah, come on, we can do better than that. What is 5, 0? It's 20. That's what I think 5, 0 should be. Now you might say, how did you do that so quickly? The answer is, I didn't look here. I looked here. F of 5, 0. Well, f of x 0 is x squared minus x. So I plugged in 5. 5 squared minus 5. 20. How about 0, 3? What would that be? Well, I can look here, plug in y equals 3, or I can plug in the top, and I can plug in x equals 0. Well, if I plug in the top, x equals 0, that's not too hard to figure out. That's 9. Okay, how about 5, 3? What would that be? Well, there's a couple places to look. I can look in the original equation, of course, plug in 5, 3. I can look on an edge. So the top edge, if I plug in x equals 5, 25 minus 20 is 5, plus 9 more gives me 14. Okay.
And will that be the same as plugging into your original function?
Yes, it will. You can plug it into anything that you found for the boundary. You can plug it into the original function, just wherever it's convenient. And now comes the inconvenient ones, because we get fractions. Yeah. Of course, well, let's see what we get. Okay, 0, 3/4. Well, that's going to be, I'm going to look on the edge. That's 2 times 9 over 16 minus 9 over 4. Well, at this point, we're sort of like, yes, that is a number. You can do a little bit better. I mean, it's 9/8 minus 18/8. So this is, if you work it out, this is actually negative, what did I say it was? So here was 9 over 8, the minus 9/4. So that's 9 over 8 minus 18 over 8. That's negative 9 over 8, which of course is negative 1.125. Sorry, I wrote a little small because I'm near the edge of the paper. The important thing is, it's not as big as negative 2 in terms of size. The thing you're keeping track of is the size. If you know it's not going to be as big as the largest number and not going to be as small as the smallest number, yeah, you don't care. You're looking for the largest and the smallest. 1/2 and 0. Well, where do we plug that in? Probably into here would be the easiest place. That'd be 1/4, 1/2 squared, minus 1/2, which is negative 1/4, which is negative 0.25. There we go. 5, 2. Well, we can plug 2 into this expression, 2y squared minus 8y plus 20. That would give us 8 minus 16 plus 20, which would give us 12. So 8 minus 16 is negative 8, plus 20 is 12. And rounding the corner, we're almost there. 2, 3. Well, let's go on the top. Plug in 2. We get 4 minus 8 plus 9. Well, 9 minus 8 is 1, plus 4 gives us 5. All right. So, to recap what we've done so far, we've found our list of points, checking the interior and checking all the boundaries. We've now plugged everything into our function. And yes, we have to plug everything on our list into our function, which is some encouragement to say, make sure things should be on the list. Don't be like, I'll just add lots of points because I like evaluating functions. Now comes the fun part. We're in the last step, the home stretch. The last step says, look at your list and find the smallest and largest. Well, what's the smallest? Negative 2. So we have negative 2. That's our global min. All right, what's our largest? 20. That's our global max. And we're done. Step 4 is the easy step, because you're just saying, look at my list of numbers. What's the biggest and smallest numbers on those lists? Okay. Well, that was fun. That only took us 18 minutes, and we have 2 to go. And that was the warm-up one. Shall we pick it up the pace for the next one? Yes, of course we should. All right. Find the global max and the global min for g of xy is x squared minus 4x plus 2y squared minus 4y plus 1 for the domain, which is a triangle. But it's not just any triangle. The vertices are at 0, 0, 3, 0, and 3, 3. So there's my triangle. And when I talk about this, I really want to be the solid triangle, not just the boundary. Okay, so there we go. There's my domain. It's closed because I'm including my edge. It's bounded because I can draw it all on the piece of paper without any problem. So I know there's going to be a global max or a global min, and I start the process. Step 1, where do we do for step 1? Find the gradient. Okay, so 2x minus 4 is the derivative with respect to x. Set that equal to 0. 4y minus 4 is the derivative with respect to y. Set that equal to 0. And if we work that out, what point are we going to end up with? 2, 1. Now, is the point 2, 1 in our domain? Well, 2, 1, if we were to sketch this a little bit more accurately, would be this point. Yes, 2, 1 is inside the triangle. So does it make our list? It does make our list. 2, 1. You've made our list. Congratulations. Now, we're done with phase 1. Step 1 is complete. We've checked the interior. What comes next? Yeah, the boundary. And we always start with the corners. Okay, so corners, congratulations. You get an automatic invite. 0, 0, 3, 0, 3, 3. You're all on the list. Okay, what's left? Well, we have the sides. How many sides now? 3. Oh, that's less than last time. So we have a bottom side, a right side, and Mr. Slanty. Okay, so which one do you want to start with? Bottom right or Mr. Slanty? Mr. Slanty. Okay. Now, previously, we were like, oh, we just plug in x equals 2 or y equals 7 or whatever it was. But notice it's a slanted side. So what do we do? Well, there's a couple of things to do. One way to do it is to say, let's parameterize. We could parameterize it. So here's a simple thing. Notice that this edge is on a line. It's on the line y equals x. And I can parameterize it by saying, for example, it's all things that look like t comma t. That's not too hard to believe. All right. Well, what does that say? Well, so if I'm on that slanted side, I can do the following. I can say that I'll look at g of t comma t. Well, again, you could do also g of x comma x or g of y comma. There's other options, but I like to think about parameterization because it's slightly more general. So that would become t squared minus 4t plus 2t squared minus 4t plus 1, which would become 3t squared minus 8t plus 1. Okay, so that's the function as a single variable. That's the point of going down a dimension. When we're on the boundary, instead of being a function of 2 things, we're a function of 1 thing. And now that we're a function of 1 thing, we use one-dimensional tools. So the derivative of 3t squared minus 8t plus 1 is, take the derivative, get 6t minus 8, set it equal to 0. And what's true about t? 4/3. So that leads to the point 4/3 comma 4/3, which is over here. Now that's on the boundary. Now, if we had gone a point over here, we would ignore it. Because that point's not on our boundary. But that point, 4/3, 4/3 is, congratulations, You've made the list. All right, 2 sides left. What's the next side you want to handle? Bottom side. All right, for the bottom side. What's true about the bottom? Yeah, bottom side, y equals 0. Okay, so that means I can really write my function as a function just of x. G of x comma 0, which is x squared minus 4x plus 1. Take the derivative, what do you get? 2x minus 4 set equal to 0, leading to us to the point x equals 2. Well, it's x equals 2, y equals 0, which is that point there. That's in our domain. It gets added to our list. All right, so we've done the slanted side, the bottom side. One more to go. The right side. What's true about the right side? X equals 3. So our function is g of 3 comma y. Well, that'll be 9 minus 12 plus 1, which means that the x squared minus 4x plus 1 simplifies really nicely to whatever it was I was going to say. It's negative 2. So it's 2y squared minus 4y minus 2. Take the derivative. Get 4y minus 4. Set that derivative equal to 0. Y equals 1. Which means, what's the point? 3 comma 1. Which is here. That's in our domain. It makes the list. All right. We double check. Have we done everything we need to make our lists? Got the interior, we got the corners, we've got all the edges. Yeah, we're good to go. Okay. So what's our next thing to do? Yeah, we get to plug all of these points in to our function. That's going to be fun. Okay. G of 2 comma 1. Well, that's 4 minus 8, which is negative 4. Plus 2 gets us to negative 2. Minus 4 is negative 6. Plus 1 is negative 5. So I get negative 5. Whew. 0, 0. What? 1. Oh yeah, that one's easy to do. 3, 0. Negative 2. We can actually come down to g of 3 comma y. And we say, negative 2. 3, 3. Well, we can come back here for 3, 3. And we can say, well, it's 2 times 9, 18. 4 times 3, minus 12. So that's 6. Minus 2 gives us 4. Alternatively, we could go over to Mr. Slanty. We could say, well, that's t equals 3. That's 27 minus 24. 27 minus 24 is 3, plus 1 is 4. Okay, 4/3, 4/3 is something. We'll come back to that one. Okay, 2, 0. What's 2, 0? We can probably do that one. 2, 0, so that's on the bottom. 4 minus 8 plus 1.
Negative 3.
Negative 3. 3 comma 1. I'll plug in 1. 2 minus 4 minus 2. Negative 4. Okay, 4/3, 4/3. Well, time to face up to it. That would be 3 times 16 over 9 minus 8 times 4 over 3 plus 1. Now, the good news is this is 16 over 3 minus 32 over 3 plus 3 over 3, which will give us what? Negative 13 over 3. Or, to make our elementary school math teachers happy, improper fractions. Negative 4 1/3. Yes? Which means this is negative 4.3333333 ... Okay. So, we've now done our evaluation. Our last step, our favorite step. Step 4. What do we do? Okay, looking on our list. Should get a color which is a little bit darker. Looking on our list. Let's do the min. Which is the smallest number on our list? -5. So, there's our global min. Happens over there. All right, looking at our list, which one's the largest? 4. Global max. Now, on a side note, what would happen if 4 showed up twice on my list? Then what's the answer? It's still 4. It's okay. It's all right to be a global min or a global max multiple times. You just take the largest value, whatever it is. All right. Well, that was a little bit faster. We have time for a third problem, which is good because we have a third problem. Find the global max and the global min for h of xy is 2x cubed plus 3y squared minus 12x for the domain x squared plus y squared is less than or equal to 4. X squared plus y squared less than or equal to 4 looks like what? It's a circle of radius 2. So, this will make it interesting when we get to the boundary. But that's to come. Let's not wait. Let's hold off doing the boundary at the boundary stage. What comes first? Gradient. By the way, I guess I should pause for a second and say, how do you know when you're doing a global max or a global min problem? The answer is, look for the words global max and global min. That's how you know you're doing a global max or a global min. They might use the word absolute. Absolute max or absolute min. It's good to know when to do things. Okay, gradient. What's the gradient? Well, 6x squared minus 12. That's the derivative with respect to x. We'll set that equal to 0. What's the derivative with respect to y? 6y. Set that equal to 0. Well, I can solve the last equation. It tells us y better be 0. What about 6x squared minus 12? Well, that says x squared better be 2. So what does that say about x? Yeah, plus or minus square root of 2. Now, square root of 2 is about 1.4. So that would say plus square root of 2 minus square root of 2. So we have those 2 points. So those get added to our list. So square root of 2 comma 0 minus square root of 2 comma 0. That's where our gradient is 0. Good. Well, that takes care of the interior. Well, next we do the boundary. All right. Well, we've started by listing the corner points. Where are the corners? There are no corners. It's nice and roundy. Wow. Cool. No corners here. Okay, so what do? Well, we have to figure out how to handle the boundary. Now, the key is to get down to a smaller number of variables. So we don't want 2 variables, we want 1 variable. And here's the thing to notice. On the boundary, x squared plus y squared is 4. Notice in our function, we only have one single y, and it shows up as y squared. So on the boundary, we can say that y squared is 4 minus x squared. So our function becomes the following. I'll call it just a function just of x. It will be 2x cubed plus 3 times 4 minus x squared minus 12x. So that's how the function behaves on the boundary. I can completely describe its behavior just in terms of x, because I'm able to use information about the boundary to reduce a variable. Now, we got lucky here today. Next time, we'll talk about what happens if you don't get lucky. We have ways to handle that. But today, we get lucky. Now, let's clean this up. Well, this becomes 2x cubed minus 3x squared minus 12x plus 12. What comes next? Take derivatives. G prime of x. Now, before we take derivatives, let's pause ever so slightly and ask, there, I have my function, 2x cubed minus 3x squared minus 12x plus 12. Is there any restriction on x? Because right now, that looks like a function which I can pick any x for. But is there any restriction placed on x? It has to correspond to the picture. Where can x go in our picture? Negative 2 to 2. So keep in mind that this is only going to work between negative 2 and 2. So negative 2 and 2 are actually, in some sense, they're endpoints. So we're going to keep that in the back of our head. Taking derivative, 6x squared minus 6x minus 12. This is looking very suspicious, as if people had planned this problem just for us to work out really nicely. What do you notice about x squared minus x minus 2? It factors. What does it factor as? X minus 2 and x plus 1. So which values of x do we care about? We care about 2, negative 1, and negative 2. Now you might say, no, you made a mistake. There's no negative 2 in there. Don't forget, you have to take in, there's essentially a corner, because negative 2 is an end. So you have to account for that as well. Okay. Now, if I'm at the point x equals 2, well, that's going to be x equals 2. That's y equals 0. Similarly, if I'm at negative 2, that's y equals 0. Now, what about negative 1? Well, if I'm at negative 1, what's true about y? Y squared would be 3, so y would be what? Plus or minus root 3. So we actually get a couple of points there. So we get negative 1 plus root 3, negative 1 minus root 3. So our list consists of these 6 points. Well, what's left for us to do? We evaluate all of these points. Ah, happy days. Okay, so I forgot the old mathematical adage, compute twice, circle your answer once. So let me retry this again. All right, so we're going to plug in x equals root 2, y equals 0. So when I take root 2 cubed, root 2 times root 2 will give me a 2, and there's one root 2 left. So that'll be 4 times square root of 2, 0, minus 12 times square root of 2, 4 minus 8 gives us negative 8 square root of 2. Now, plug in negative root 2. Well, what changes is that this will change sign because of the cubed, and that will change sign, and that's still 0. So if you work it out, it's still going to be 8 root 2, but now positive 8 root 2. Now, if you're not convinced, go ahead and work it out longhand. So you're going to get a negative 4 root 2, positive 12 root 2, negative 4, positive 12 gives us 8 root 2. So we'll plug in 2 comma 0. So it'll be 2 cubed is 8 times 2 is 16. Then I'm going to take negative 24, 16 subtract 24, negative 8. Plug in negative 2 comma 0. Well, there we'll get negative 2 cubed is negative 8 times 2 is negative 16. Still have a 0 here. Don't worry, it'll come into play. And then we have positive 24. Okay, so it's going to be positive 8 is the total contribution. And now we come minus 1 square root of 3. Ah, good. Y has something. It's going to be interesting. So when we plug in the x, we're going to get negative 1 times 2, so that's negative 2. Then we get 3 times square root of 3 squared. Well, square root of 3 squared is 3, so 3 times 3 is 9. So negative 2 and 9. That makes 7. Then we're going to subtract 12 times negative 1. Well, that's really plus 12. 7 and 12 together make 19. All right, so that's 19. And, well, you can see the x is the same, and the y, even though it's negative, we square it, doesn't make a difference, still get 19. Okay, so those, that's the values. All right, now we need to decide smallest, largest. Well, largest. We have 2 candidates. Well, a few candidates, 8. 8 root 2, and 19. Well, look, 8 is definitely smaller than 8 root 2. And 8 root 2, well, that's definitely smaller than just 8 times 2, which is 16. And that's smaller than 19. So 19, that's the largest. So that's our global max. And notice, this is a case where we achieve 19 at 2 different locations. That's okay. It's okay to have it occur at multiple locations. Okay, smallest global min. Well, we have -8, -8 root 2. Well, because root 2 is bigger than 1, when I multiply -8 by root 2, I'll end up with something even more negative than just -8. So that's our smallest, our global min. All right. So global min, -8 root 2, global max, 19. And that's it. All right. Well, good. Now we know how to find global mins and global max. Remember, Santa Claus approach. Make a list, check it twice, plug it in, and now you're going to find out which points are naughty and which points are nice.